All right, we're going to talk today about matrices and systems of linear equations. So let's start with a definition. And M by N real matrix is a rectangular array of M rows and N columns of real numbers. It's as simple as that. Remember our definition of a vector as a pair, a triple, a quadruple, and so forth. And we left it at that, just an ordered pair. Same thing with a matrix. So in a way, a matrix is an extension of a vector. In a way, every vector is a matrix, but not every matrix is a vector. So let's look at some examples. So A could represent a matrix, and we can have it as you know 3, -7, 0, 2, 5, and 1, and we don't put commas, we just put spaces so it is clear which one is which. So this is a matrix that is 2 by 3 is a 2 by 3 matrix because it has 2 rows and 3 columns. If you're missing one entry, then you don't have a matrix. You can replace entries with variables. That is all right. But we have to have a rectangular array, and every part has to have something in it. If there is something missing, then we don't have a matrix. So if this was if there was an empty spot here, that wouldn't be a matrix. If we put a variable and we wouldn't, without knowing the value of the variable, that is okay. But we have to have um, a rectangular array of matrices. So all the rows have to have the same number of elements, and all the columns have to have the same number of elements. And two matrices of different size they technically belong to different worlds, just like with vectors. They're not really part of the same thing. So if we have, let's just write an example. So say B equals 3, -7, 2, and 5. That matrix has nothing to do with that one. If anything, we would just say that it is a coincidence that the 2 columns here are the 2 columns there, but that they share 2 columns. I guess we could say that, but that's about it. This is a 2 by 2 matrix. Matrices for which the number of rows is the same as the number of columns are called square matrix. So a square matrix. So this is a square matrix. This is not a square matrix. We assume both are rectangular matrices. So the smallest matrix you can have is a 1 by 1, and then, which again, we don't talk about 1 by 1 matrices because that is confusing. It isn't prohibited. It isn't that we cannot. It's just confusing. So we don't talk much about 1 by 1 matrices. You can have 1 by 2 matrices. So that would be just like a row. So let's say, yeah, let's write an example. 3, example 3. So if you have the matrix C, 3, -7. Here we tend to put a comma. Sometimes we put a comma, sometimes we don't, because they're just together. If it is clear we have only two elements, then there is no need for the comma. Um, so this is a 1 by 2 matrix, also known as two-dimensional row vector. So yeah, so you can have so again, a vector, which is a pair of numbers that are ordered. There it is. A matrix is a rectangular array, and we have only one row and two columns, then that's the same thing as a vector. Yeah, we typically use capital letters to denote matrices. Some people use parentheses, round parentheses. Some people use square parentheses. So if we write C as 3 -7, I don't think there is any difference. Some people may think, well, yeah, I don't make any difference. And I guess we could use some other kind of parenthesis, as long all we're doing is keeping it all together with this sort of grouping symbols. So in my classes, I don't differentiate between this or that or that. And the same thing happens with regular matrices. So for instance, B, so we're talking about notation now. So B, if you put a rectangular as opposed to a round parenthesis around it, 3 -7 2 5, it's the same thing as the B we had earlier in example 2. Yeah, there's no difference. I don't see this notation often with matrices, but I don't see why not. We can just do this. So most people use rectangular or round parentheses, and I don't think it makes any difference one or the other. It is reasonably clear that we are dealing with matrices when we are doing that. So let's talk about addition and subtraction. Addition and subtraction of matrices. We can add matrices only if they are exactly of the same size. So the same dimensions, not only the same size, but the same dimensions. So for instance, we can add what was A, 3 -7 0 2 5 1 with another matrix. Now, if we add with another matrix, this matrix has to be a 2 by 3 matrix. It cannot be any other size. So let's put some random numbers such as 0, 1, 2, 3, 4, 5. I guess they're not so random. But so if we wanted to add those two matrices, the addition is pretty straightforward. Just add corresponding components. So 3 plus 0 is 3, -7 plus 1 is -6, 0 plus 2 is 2, 2 plus 3 is 5, 5 plus 4 is 9, 1 plus 5 is 6. And that's the end of it. There's not much drama to it. All you have to do is keep track of what you're adding together, and then you're done. So adding is very, very straightforward. Subtracting is almost as easy. So example 5. Let's copy the same matrices. So 3 -7 0 2 5 1 minus 0 1 2 3 4 5. Boy. There, that looks a little better. And as you can probably tell, what's going to happen is that we're going to subtract corresponding coefficients or coordinates, entries. So 3 minus 0, 3, -7 minus 1, -8, 0 minus 2, -2, 2 minus 3, -1, 5 minus 4, +1, 1 minus 5, -4. And there it is. Okay. We can multiply matrices with a scalar. Multiplying with scalars. So in a way, this is very much the same as a vector when you think about it. So let's take our old matrix. So example 6, if you have 3, -7, 0, 2, 5, 1, we can multiply this by any number you want, 2. So this is a scalar times the matrix. And just as with the vectors, we multiply every entry by that scalar. So 2 times 3, 6, 2 times -7, -14, 2 times 0 is 0, 2 times 2, 4, 2 times 5, 10, 2 times 1, 2. There we go. And likewise, you can, as much as you can multiply into a matrix, you can factor things out of a matrix. That is very handy when we are doing computations. So for instance, 3, -8, -2, -1, 1, -4. So this matrix has 4 negative numbers. Perhaps we can factor out the negative out of it. It's really -1, but we don't put the 1. And so this would turn into -3, 8, 2, 1, -1, 4. And somebody may ask, well, why would you want to do that? There's a couple of reasons, but a simple one is here, this matrix has 4 negative numbers. This matrix has only 2 negative numbers. And so that could be perhaps easier to work with. And you don't have to factor just negatives. You may factor anything that is common to all the elements in the matrix. So multiplying and factoring is good. Now, we are going to do things with matrices later, such as finding the determinants. And we got to be careful because determinants are affected by rows or columns. Well, we cannot find a determinant of this matrix. The determinant is something we're going to see in the future. So if you're not familiar with determinant, don't worry. This is in the future. But what I want to tell you ahead of time is that determinants are established by rows and columns. But if we have a 2, an extra 2 on each row, then the determinant gets multiplied by as many 2's as rows we have. So we just got to keep an eye on the computations when we multiply by scalars. All right, so we can add, subtract, and we can multiply by a scalar. So that means that we can have linear combinations of matrices. Linear combinations of matrices, just as we did with vectors. So for instance, example 8, I'm going to use a smaller matrix just because 2 by 3 gets kind of big on this page. But let's say you have 3 times the matrix, 4, 7, 0, -2. And then we're going to add 5 times the matrix, 0, 1, 2, 3. Okay, so that's a linear combination of those 2 matrices. Whether you add or subtract, and whatever numbers you want to use, you can use 0 for one of the scalars. Whatever numbers you want to use, we will end up with a linear combination of those matrices. So let's go ahead. Now, when you are doing computations, especially when you're turning in an assessment, double check your work, go slowly, show your steps, because you don't want to make mistakes and lose points on the assessments. I don't think the assessments will be particularly difficult in this class, but we want to be careful. So I'm going to violate that rule. I'm going to not be too careful and do 2 steps, actually 3 steps in one. I'm going to multiply with a 3. I'm going to multiply this matrix with a 5, and I'm going to add all together at once. Don't do that in assessments because you may lose points. So 3 times 4 is 12. 5 times 0 is 0. 12 and 0 is just the 12. Okay, 3 times 7 is 21, plus 5, 26. 3 times 0 is 0, and 10, 10. 3 times negative 2 is negative 6, and 15 is 9. And there we have it. So I did a couple things all at once. Multiply the 3 with this matrix. So we end up with 12, 21, 0, negative 6. Multiply the 5 with this matrix to end up with 0, 5, 10, 15. And then I added all those together in one shot. I mean, oh, please do not use calculators. A graphing calculator will do that. Well, my calculator is missing batteries. The batteries are low in my calculator, yes. And you can set matrices, and you can enter matrices in the calculator, and you can figure out linear combinations and other things with a calculator. But the matrices we're going to work on are small enough, 2 by 2, 3 by 3. And if we go into higher dimensions, such as 4 by 4 or 5 by 5, they shouldn't be too difficult to work on. And so using a graphing calculator defeats the purpose of the exercise, the practice we need to do with those matrices. So please avoid using graphing calculators unless you're checking your work. If you want to check your work, that is okay. That is fine. Okay. So now let's talk about multiplying matrices. Multiplying matrices. Okay. So if we multiply matrices, so there's a matrix 1 and a matrix 2, and we want to multiply them together. We are able to do that only when the matrix, the first matrix, has dimensions little m by n, whatever those numbers are, but the second matrix has to have dimensions n by p. What I mean by that is the number of columns of the matrix on the left has to match exactly the number of rows on the matrix on the right. So I'm going to write that down. So this is the number of columns of matrix on left of the multiplication. And that number has to be exactly the same, no more, no less, as the number of rows of matrix on right. Okay, it has to match. Now, those other two numbers, the number of rows of the left matrix, the first matrix, and the number of columns of the second matrix, they can be any number. It doesn't matter what they are. What is important is that those two are identically the same number. So let's continue doing more examples. Example 9. Let's say we want to multiply the matrix we've been dealing with for a while, 3, negative 7, 0, 2, 5, 1. Okay, so the second matrix, 2 by 3, has to be 3 by something. Let's keep things simple. So 0, 1, 2, 3, 4, 5. There we go. The resulting matrix of this multiplication will be a matrix that is, in general, M by P. M by P. So this is 2 by 3. This matrix is 3 by 2. So that means multiplying this matrix in this direction is in this way will be okay because those two match. Those two match, but that is a coincidence. The important thing is that the number of columns of the matrix on the left matches the number of rows of the matrix on the right. All right, so we're going to end up with a matrix that is going to be 2 by 2. Whatever this number is, by this. So we're going to have a relatively small matrix, 2 by 2. And the way we obtain the entries is by dotting the product or applying the dot product of rows and columns in that order. Rows and columns in that order. So rows for the left matrix, the first matrix. So I'm going to call this the first and that the second matrix because as we read from left to right, that's the first one and that's the second one, okay? Instead of calling them left and right. So for the first matrix, we're always going to use rows. And for the second matrix, we're going to use columns. And that's the rule. That's the way we're going to do it. So what is the dot product of, I'm looking for a pencil. I thought I had one. Anyway, what is the dot product of this row and this column? Well, let's see. 0 minus 14 plus 0. So negative 14 is the dot product of that column, that row rather, and that column. So 1, 1. The second element on the right, on the first row of the product will be the dot product of that row, the first row, and the second column. So that is going to be 3, negative 21, and 0. 3, negative 21. So that is going to be negative 18 because then we have a 0. There's no room for that here. So I'm just going to write the answer down here. Okay, so multiplying those two, negative 14, negative 18. And then to find this element here, we use the second row because the element here is on the second row of the answer. But the element here on the end of the answer is on the first column of the answer. So use the first column of the second matrix and multiply, use the dot product. That's why, by the way, this number has to match this number because otherwise we wouldn't be able to do the dot product of this row with this column. So we have 0, 10, 4. 0, and multiplying 2 times 0 is 0, 5 times 2 is 10, 1 times 4 is 4. So, and then we add those products together, 0 plus 10 plus 4, 14. And then to find this element, which is on the second row and second column, multiply the second row of the first matrix and the second column of the second matrix. So 2, 15, 5. 2, 15, 5. 2 and 15, 17, and 5 is 22. There. So that is the multiplication of those two matrices. Something that I noticed right away is that all of them are even numbers. So we could factor out, as we learned in the previous page, 2, and that will keep things a little simpler. Negative 7, negative 9, 7, 11. Yeah. That is interesting because this matrix has no this matrix is not completely full of even numbers. It actually only has 2. And this matrix doesn't have as many either. There's 3 odd numbers and 3 even numbers, and yet the multiplication is full of even numbers. That is interesting. And I think that is just a coincidence at this point. Um, so that is how we multiply matrices. We're going to multiply the same two matrices, but in the reverse order. That is going to be our example 10. So we're going to multiply 0, 1, 2, 3, 4, 5 with 3, -7, 0, 2, 5, 1. Okay. And let's see. How do we multiply this? Well, this is a 3 by 2 matrix. 3 by 2. This one is a 2 by 3 matrix. Those two match perfectly. So that means that we are able to do the multiplication. Furthermore, the multiplication will end up with a matrix that is going to be 3 by 3. So we're going to have a pretty large matrix, a square matrix. This one, by the way, was also a square matrix. But this is a 2 by 2, while this one is going to be a 3 by 3. So, okay, so this is going to be a 3 by 3. The first element is going to be the dot product of the first row on the first matrix with the first row on the second matrix. So 0 plus 2. And then we move on. Negative, or rather 0 plus 5. 0 plus 1. And then we move on to the next row. Or that's the way I do it. You don't necessarily have to go in this particular order, but this is the way I do it. So 6 and 6. -14 and 15. 0 and 3. Now move on to the next row. 12 and 10. -28 and 25. 0 and 5. There. Let me double check one more time. 2, 5, 1, 6 and 6 is 12. -14 plus 15. 0, 3, 12, and 10. -28 plus 25. 0 and 5. It appears this is correct. Yeah, and this is not a matrix full of even numbers, so we cannot factor out a 2. I mean, we could, but then we would have to introduce fractions. So it is simpler just to keep it the way it is. So notice that we did use exactly the same matrices in different order, and we obtained a different answer completely. This proves, this is an example of why multiplication of matrices is not commutative. So this is a fact. Multiplication of matrices is not commutative. Now let me elaborate on that. What does commutative mean? Commutative means that the order in which we multiply, because we're talking about the multiplication, does not matter. It never matters. So commutative means that order never, ever, never matters. Okay, it never, never, ever, ever matters. What is the opposite of never, never, ever something? It's Yeah, let's talk about that. Negating, um, yeah, yeah. So here's the question: how do we negate never, never, ever, never, question mark? I, this is a little bit of a joke. It's never is sufficient, but I'm just putting never, ever, never to be a little funny. But anyway, um, how do we negate that? Some of us may be thinking, oh, well, isn't the negation of that always, always, always? And the answer is no. Uh, the answer is at least once. So the negation of that is, so the answer is at least once of whatever we're talking about. So if I tell you I never ever 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 make a mistake, um, what is the negation of that? Of course, if I tell you that, that would be a complete lie, that I never make a mistake. Um, yeah, yeah. So the negation of that is that at least during my life, I made one mistake. It isn't that I always make mistakes. The negation of I never make a mistake isn't that I always make mistakes constantly, every moment of my life I make a mistake. That is not the negation. The negation is that I make a mistake at least once. Yeah. What I claim is that I make a mistake. This is more for real. Well, it's half joking. I make a mistake um, about on average once an hour, which is about, I think it's about right, even when I'm sleeping. So yeah. So be careful. The reason why I'm bringing this up is because of the commutative. Commutative implies that the order never ever matters. When we say that something is not commutative, what does that mean? That means that there's at least one instance when the order matters. But it could happen that there are instances where the order does not matter. So we got to watch out. So not commutative means the order never, ever, ever matters. Not commutative means that the order matters at least in one instance. Actually, it matters in many instances, but that doesn't mean that it always matters. Let me give you another example. Example 11. Let's say you have the matrix 0. Actually, I meant to put 8, 0, 0, 3 multiplied with, let's keep things simple, 1, 2 rather, 5, and then zeros in this. Okay. So the product, let's try to fit it in here, will be 16 and 0, 0 and 0, 0 and 0. This is interesting that we get zeros because when we do the dot product, if this is 0, that causes the product of those two to be 0, regardless of what this number is. And then when this is 0, whatever this number is, it causes the product to be 0. So we end up with 0. When this number is not 0, this number is 0. When this number is not 0, this number is 0. So we always get 0. And then 0 and 15. Okay. Now let's do this product the other way. 2005, 8003. And then we have 16, 0. Let's make sure 0, 0. Yep. 0, 0, 0, 15. So in this case, when we change the order of the multiplication of the matrices, the order did not matter because we end up with the same answer. So occasionally it is true that the order doesn't matter, but there's at least one example example 8 and 9, no, 9 and 10 rather, yep, 9 and 10, show that the order matters. Yeah, yeah. So we gotta be careful with the always and never kind of thing, because the negation of those statements is not the always. It can be that there is at least one example for which it doesn't work. That is an important concept in all of mathematics, the never and the always. Always ask yourself, is this statement applied to always or to never or occasionally? And if it doesn't apply to always, then can we come up with some counterexamples? For instance, this one was a good counterexample. It's a fairly large counterexample, 9 and 10. Nonetheless, it is still a counterexample. Okay, there's many counterexamples, I suppose. Um, let's switch gears a little bit and talk about systems of equations, and then we're going to connect the system of equations with a with matrices. So let's talk for a moment about system of equations, and by that we mean of linear equations. Technically, we should write that down: linear equations. Um, so let's say you have 3x minus 7y equal to some random number such as 17, and then 2x plus 5y. We're not going to solve this system. This is not. So even though this is an example, 12, I'm not going to solve this system. Plus z equals 18. I'm just picking some random number that is kind of easy. And I guess I don't have too much imagination. So what is the number after 17? And that is 18. And that's why I picked 18. All right, so this is a system of equations, 2 equations and 3 unknowns. X, Y, Z. I forgot if I told you, I cross my Z's to distinguish them from 2s. Otherwise, sometimes my 2s and my Z's look too much alike. So I just cross the Z's to tell them apart. Okay, so we have 3 variables and 2 equations. This is a typical standard system of equations. And the thing is, we can rewrite the system of equations or paraphrase the system of equations using matrices. Yep. If we multiply 3, -1, 0, 2, 5, 1 with the matrix x, y, z equaling the vector or the matrix 17, 18, those two represent exactly the same idea. Why? Because if we multiply those two matrices as we just learned how to do, then we end up with 3x minus 1y plus nothing. Okay, so this is a 2 by 3. This is a 3 by 1. 2 by 3. 3 by 1. Those two match, so we're doing the right thing. And the answer, the product, will be a matrix that is 2 by 1. So only 2 entries, even though this looks like there are 2 within this one. This is just 1. I'm going to circle it just to show. This is just 1 entry. And then the next entry, which is kind of long too, it will be 2x plus 5y plus, so 2x plus 5y plus 1z. Again, this is just 1 entry, as long as it looks, equaling 17, 18. And I didn't make a big deal about this before, but 2 matrices are equal exactly when the entries, their corresponding entries, are identically the same. So this means that, so 3x minus, oh, here I made a mistake. See, speaking of mistakes, this should be a 7. Yep. And so when we multiply, that should be a 7. There we go. So 3x minus 7y, this entry has to be equal to that entry. This is a 2 by 1 matrix, 2 by 1. And the only way they can be equal is if the corresponding coefficients or the corresponding entries are equal. So this entry has to match identically 17. And then this entry, 2x plus 5y plus z, has to match identically 18. So there. This system of equations comes from this equation of matrices. And that happens a lot. So there is a strong relationship between matrices and systems of linear equations. Yes, yes. Okay, let's do more with that now. Example. Oh, there's something I forgot to mention, so I better not miss that. Some notation about matrices. So more notation about matrices. And I'm not going to give you a complete list of all the kinds of matrices there are. Any book you read will have some kind of explanation of some kinds of matrices. There is triangular matrices and other kind of matrices that perhaps we will define more in detail in future videos. Um, so I'm not giving you a complete list of all the characteristics of a matrix, but it is not too difficult to read those characteristics in just about any book. If you have a matrix, let's just, for simplicity, call it a square matrix. The element on the upper left corner is labeled as A. If we use the letter A sub 1, 1. Technically speaking, there should be a comma because this is not 11, it is 1, 1. But it gets kind of small, so I just omit the comma. So that means that this element belongs to the first row and first column. The element on the first row and second column will be labeled as 1, 2. 1, 3, first row, second column. So the one underneath will be 2, 3. Second row, third column. A, 2, 2, second row, second column. I don't know if I mentioned this correctly. Second row, third column. Second row, first column. Third row, first column. Third row, second column. Third row, third column. So this is the standard way of denoting the elements of a matrix. A sub 1, 1. So this oftentimes is labeled as A. And then we use the same letter for the elements. The elements in this diagonal are called the elements on the main diagonal. Or I guess I should have said that is labeled as the main diagonal because there's two of them. So this is the main diagonal of the matrix. And I already mentioned this is a square matrix. And that's about it. Yeah. We can, again, sub-classify matrices into upper triangular, lower triangular, and so forth. Let's do more examples about systems of equations. So example 13. Okay. So let's say we have the matrix equation 1, 3, 2, 5 x, y equal to 17, 18. Okay, so this is a new problem altogether. And we want to solve this problem. We want to solve this equation. You know, when we solve equations, linear equations in algebra 1, you know, we had a number times x times an equals to another number. So just to give you an example, you know, back in algebra 1, you had problems like yeah, 3x equals 24. So you solve for x, and x has to be, in this case, 8. So that's what we're going to do, except that these are not numbers. These are matrices. So we want to know what this matrix is. You know, pretend you have something like 3x equals 24. So this matrix times x, y equals this other matrix. Well, what is this matrix? You know, what is the value of the variable matrix in this case? Well, let's do it the translation way. Let's translate this into a system of equations. So we got x and 2y, x plus 2y equals 17, and then 3x plus 5y, 3x plus 5y equals 18. Okay, and then if we want to solve for x and y, now we know how to do this. This is from algebra 1 or algebra 2. We can multiply this equation by 3 times 3, and we get 3x plus 6y equals 51. And then we can subtract. So the 3x's go. 5y minus 6y is negative y. And then 18 minus 51 equals 18 minus 51 is 33, if I'm not mistaken, negative. I think that is correct. So y equals 33. And then we need to find x. So one way to go about that is to say, well, x is from this equation, 17 minus 2y. So that would be 17, but we just realized y is 33, so 2y is 66. So we need to take away 66. So 16 minus 7 is 9. 5 minus 1 is 4. And we end up with a negative. Okay. So xy is equal to negative 49, positive 33. There we go. So we were able to solve this. We actually gave a solution. Negative 49 plus 66 equals 17. I want to double check this to make sure it makes sense. So if we multiply those, the negative 40, well, let's do it. Let's check. Okay, so 1, 2, 3, 5 multiplied with negative 49 and 33. Well, let's see. That's going to be negative 49 plus 66, and then negative 147. Boy, 15, carry 1, 16, 165. And we're going to add that. This is not a 2 by 2 matrix. This is a 2 by 1 matrix. We still have to subtract. So 16 minus 9 is 7. 5 minus 4 is 1. 15 minus 7, 8. 15 minus 14 is 1. Sure enough, it works. So that means this answer that we gave is the correct answer because we just double checked it and it works. Okay, so this is one way to solve this equation. This is great. 14, this is going to lead to something that is important that you need to know for the homework that we are assigning. Let's say you have 1, 2, 3, 5, x, y, and now some other random numbers. Let's say 10 and 20. Just out of the blue, I'm thinking right now, okay, 10 and 12. Same kind of system of equations, 1, 2, 3, 5, x, y, 1, 2, 3, 5, x, y. Instead of 17, 18, now we have 10, 20. I'm changing the output of this product. And let's go ahead and solve it. Well, we have x plus 2y equals 10, 3x plus 5y equals 20. One thing you could do is pause the video and then solve it yourself and get ahead of me. 3x plus 6y equals 30. And then we subtract negative y. 20 minus 30 is negative 10. So y equals 10. That is a coincidence. And x equals 10 minus 2y. So, oh, that is equal to 10 minus 20 because y is 10. That is negative 10. So xy is negative 10, 10. And we can factor the 10 out. So this is the answer. Or we can factor it out, the 10, and have negative 1, 1. Interesting. Very, very interesting. Yeah, and it would work. Now, let's pretend, well, let's do one more. 15. Example 15. 1, 2, 3, 5, x, y. Another set of random numbers. How about, let's put a negative number somewhere in the picture. How about 6, negative 7? Okay, so again, we go through the same process. X plus 2y equals 6. 3x plus 5y equals negative 7. And then you multiply the first equation by 3. 3x plus 6y equals 18. But then we subtract, and negative y equals negative 25. So y has to be positive 25. But then x equals 6 minus 2y. In this case, we have 6 minus 50. And that is negative 44. So xy is equal to negative 44 because that is the x value, and 25, and that should work. Now, pretend I was gonna give you, 50 of these problems. Exactly the same. The only thing different is that I'm gonna be changing those numbers. So just like we did with problem number 13, same setup, but 17, 18, 10, 20 in example 14, 6, negative 7 in example 15, and so forth. If we make too many of them, too many of the same kind of problems, we want to find a way to mass produce the solutions. So this is my way of thinking. Yeah, if we were to have, many more of the same, comma, the question is, how do we mass produce solutions? Yeah, that's a good problem to ask. We ask that kind of problem in math frequently. There we go. Okay. So let's answer that question. Let's make an example out of that. Example 16. All right. So if you knew in advance, you know, if you could not go to recess until you did, I don't know, 30 of these different problems, where we're changing those numbers, that matrix, with another number, another number, another number, another matrix. You might be thinking, wait a minute, instead of doing one by one, why don't I just do a generic one? Whoops, not with A and B, and then try to come up with a formula for it. There we go. Yeah, so let's do the generic system of equations where those two are constants, and we got to figure out what x and y works. In this case, it was negative 44 and positive 25. In this other case, I still remember it was negative 10 and 10. Up here we had negative. Well, the first number seems to be negative and the second one positive. That is a pattern that is going on, and it seems to be reasonably consistent. Maybe there is something to that. Well, let's just go through the motions. So x plus 2y would be equal to a. So we're going to solve this system once and for all for every single one of those two numbers. 3x plus 5y equals b. Okay. So we go through the same motions as we did before. 3x plus 6y. You almost memorized this by now. It's 3a. And then we subtract negative y equals b minus 3a. B minus 3a. So that means that positive, well, not positive, the opposite, which is regular y, will be 3a minus b. Okay. And then x from there is a minus 2y, but we already know that y is 3a minus b. So we have a minus 6a plus 2b. Let's see. So 2b minus 5a. All right. So xy will be 2b minus 5, whoops, minus 5a okay, minus 5a, and y is 3a minus b. Whoa, so now we can do this. Just apply this formula instead of going through the same process every single time we're doing this problem. Now, this is if you knew in advance you were going to do a whole bunch of them. But even if we didn't know in advance, it is good to know how to do this. It is very, very important. Now, let me test this formula with this example up here. So a is 6 and b is negative 7. Okay, so negative 14 minus 30, negative 44. Sure enough, we got negative 44. A is 6, so that is 18, plus 7, because we got a double negative, 25. Sure enough, that's the answer we got here. So just checking with this example 15, it looks like we are correct. But there is more to this. So we're going to continue with this example, 16. Continue. Okay, so let me copy this down. Xy is equal to 2b minus 5a, 3a minus b. Actually, I'm going to rewrite this. I'm going to keep them in order. So 5a negative plus 2b and 3a minus b. And the reason for that is because we can rewrite this matrix as the matrix negative 5, 2, 3, negative 1 multiplied with a, b. All right, so let's just make sure. Negative 5a plus 2b, 3a minus b. Sure enough. So this is what we're getting to. If we have a system AX, where X is a vector, equals B, and B is another column vector, and A is a matrix, okay, such as 1, 2, 3, 5, X, Y equals A, B, we may solve for X, Y by multiplying negative 5, 2, 3, negative 1 with a, b. Consequently, we may write X, the vector X, as this new matrix times B. We're going to label this new matrix as A to the negative 1, B. And this is the inverse matrix of A, which A, this one. This is the inverse of that matrix. Exactly, precisely. Why? Because it solves the equation. Okay, let me back up a little bit and tell you more about inverses in general. So, inverses in general. Very important concept in algebra. So, let's say you have an equation, x, well, let's put the 5 before. 5 plus x equals, I don't know, 17. So this is just a random equation. You know how to solve this equation. We subtract 5 from both sides. But the other way to think of it is add negative 5 to both sides of the equation. So now we're going to have negative 5 plus x equals negative 5 plus 17. So we go from this equation to this equation by adding negative 5 to both sides of the equation. Of course, we're going to end up with 0, which does not affect the addition. Zeros do not affect addition. So x is equal to, and then here we compute this addition. And of course, the answer is 12. So because negative 5, in this case, allows us to solve this equation, we label negative 5 as the inverse of 5 with respect to addition, because it allows us to solve this equation for x. On the other hand, if you have 5x equals 17, so this is a new example, how do we solve the equation? Well, you know from algebra 1, divide by 5. But the other way to think of it is multiply by 1/5 on both sides of the equation. That causes us to have a 1, and 1 does not affect multiplications. 1 is neutral under multiplications, just like 0 is neutral under addition. So we end up with 1x equals, and then 17/5. And then we actually do the operation here. Because of that, 1/5 is labeled as the inverse of 5. So far we have the same name, inverse of 5, inverse of 5. But this is with respect to multiplication. So this is a little informal the way I'm going to say it, but the inverse allows us to solve the equation depending on the operation. So when somebody says, what is the inverse of 5? You got to pause and say, wait a minute, that question is unfair. You have to tell me inverse with respect to what operation. The inverse by itself is a relative, very, very relative term. There's inverses depending on the operation. The concept of inverse has to do with the operation. So what allows us to solve for the operation, and that is an informal way to state it. There's a much more formal, better way to state it. But the informal way to say, to figure out what an inverse is by figuring out how to solve an equation. Yeah. So when we have a matrix A multiplied with a vector x, giving us another vector b, and we want to solve for x, well, we can do the same thing. But in this case, we need to multiply by a second matrix that is going to allow us to solve for this. And the second matrix is going to be the inverse. So x is going to be this new matrix, which is not the same as that one, just like 1/5 is not the same as 5, or -5 is not the same as 5. They're different. They have something about it, but they're different. B. So this is called the inverse of matrix A. Technically speaking, we should state with respect to multiplication of matrices. But of course, that is too long to say, and it is understood. So this part, when we say inverse of a matrix A, the operation in this case is understood. Yeah. And here we don't say, this is a little bit too long to say, so also known as opposite. So we call the inverse of 5 with respect to addition opposite, and that saves us a lot of wording. And the inverse of 5 with respect to multiplication has a special name, reciprocal. Yeah, so, but the initial name is inverse for all three. If we are talking about addition, then we call it opposite. With numbers, if we're talking about multiplication, we call it reciprocal. If we have matrices, we just call it inverse and leave it at that. If we want the inverse with respect to the addition, we just call the opposite matrix. Yeah. Yeah. So this is a new matrix. And as you can tell, it is not easy to figure out what the new matrix. Yeah. Okay. So based on what we just did. Okay. Thus, 1, 2, 3, 5 inverse is equal to, and I'm bringing this back from the example we finished, -5, 2, 3, -1. And figuring this out is a process, the same kind of process as we did when we were actually solving the system of equations in general. Okay, so this is the inverse. This is the inverse of the matrix 1, 2, 3, 5. Yeah, it would be totally wrong just to say something. it would be totally wrong to say 1, 2, 3, 5 inverse equals 1, 1/2, 1/3, 1/5. Totally wrong. Don't. That is a joke. If you did that, either you're joking or you don't know what's going on. So I'm anyway. No. There's a process to figure the inverse, and we're going to get into how to find inverses more in detail later. There's one other thing I wanted to mention before we finish this video, and that is the identity matrix. Identity matrices, there's a couple other things I need to say. The identity matrix is the matrix that has ones in the main diagonal and 0 everywhere else. And we have to have a square, only square matrices can be identity matrices. And the thing with this is that no matter what you multiply with, negative 7, 2, 3, 0, 1, 8, I just came up with that right now. If you multiply an identity matrix with any matrix for which the size works, so if this is a 3 by 3, this one better have 3 rows, and it doesn't matter how many columns, in this case 2, you're going to end up with exactly the same matrix. So the identity matrix is neutral relative to any other rather, it is neutral relative to multiplication of matrices. So that is an important matrix to remember. This is a 3 by 3 identity matrix, and you have a 2 by 2 identity matrix, and a 4 by 4, and so forth. We don't talk too much about 1 by 1 matrices because that could create some confusion, because then that is almost the same thing as talking about the scalars themselves. So what is the point of talking about matrices if they don't add complexity to them? It would be a trivial case. I forgot what I was going to mention also, but I think we can stop here this video. So we will do that. All right.